Welcome to Prospective Doctors MCAT Podcast, brought to you by Med School Coach. Each week, Sam breaks down the highest yield MCAT topics so you can score as high as possible on test day.
Hello and welcome to Prospective Doctors MCAT Basics with your host Sam Smith. The goal of this podcast is to cover the highest yield topics on the MCAT and provide you with some sort of insight into the questions that the MCAT really likes to ask. In addition, I'll tie in some of the testing strategies that I and other students have used on the MCAT. This podcast is going to cover electricity and magnetism, which is the theory that underlies one of the most important physics topics on the MCAT, which is circuits. And a podcast about circuits is going to be a whole podcast on its own. This one's just going to talk about electricity and magnetism because it's still a pretty important topic to understand for the MCAT. You will see at least a few questions about either electricity or magnetism or both. So still an important topic, don't write it off. And the bulk of this material will be found on the physics and chemistry section of the MCAT. So it's 1 out of the 4. You might see some of this on also the biochem, just maybe a little bit of a circuits topic or something like that. But mainly it's going to be focused on the chemistry and physics portion of the MCAT. So without further ado, let's get into electricity and magnetism. So let's talk first about electricity. The first thing to understand about electricity is charge. First of all, what is charge? Well, charge is the physical property of matter that causes it to experience a force when placed in an electromagnetic field. And this charge can either be positive or it can be negative. For example, an electron obviously has a negative charge, positron has a positive charge. And it's long been known that charge exists. So specifically a long time ago, people noticed that cloth could become attracted to certain different types of material. Specifically, cloth would become attracted to this substance called amber, which is fossilized tree resin. And what happened is when they rubbed them together, they found that when you took this cloth and you put it near this piece of amber, that they were actually attracted to each other, that this cloth would want to actually stick to that amber, which was strange, right? They didn't really know why that was. And this was super long ago, right? Even Plato talked about the quote-unquote wonderful attracting power of amber. And this phenomenon called the amber effect was likely observed long before recorded history, so it goes way back. And what this has to do with is separation of charge and static electricity. And so I'm going to go into those first, but this actually has a lot to do with charge, which was formally discovered by Benjamin Franklin. And he's the one that you can thank for defining positive charge and defining negative charge. And what he actually believed was that positive charge was just an excess of charge, whereas negative charge was an absence of charge, which today we know is not quite true. So again, charge is a physical property of matter that causes it to experience a force when placed in an electromagnetic field. So for instance, when you place positive and negative charges in electric field, they feel opposite charges to one another. They feel opposite forces to one another, right? So a positive charge, let's say, feels a force that pushes it away from you. Well, then a negative charged particle will feel a force that actually pulls it towards you. So they feel opposite forces in the same electric field. All right, so I'm going to discuss charge in 2 different ways. The first is with standing charge or still charge, also called static charge. And then I'll talk about moving charge, which produces current. So let's start with static charge. There's a few different important things to know here for the MCAT. So let's think back to the example of the amber effect. And so the amber effect is analogous to these demonstrations that you've probably seen in physics class where you take this rod of usually some kind of plastic or something like that, and you actually rub it with a cloth. And then you take this charged rod now that becomes charged after rubbing it with this cloth, you use to actually roll an aluminum soda can. You put this rod up close to it, and this rod pulls that aluminum soda can towards it, which causes it to roll. And if you don't know what I'm talking about, then either you didn't take intro physics, which is unlikely, or you didn't have a cool physics teacher. So if you didn't have a cool physics teacher or you don't remember it or whatever, just go type it in YouTube, and that way you'll understand kind of what I'm talking about. This demonstration illustrates a few really important principles to understand about static charge for the MCAT. And that is triboelectricity, conservation of charge, electrostatic force, and then also insulators and conductors. And so I'm going to break these down, talk about each of these in the context to this example that I just gave, and where you might see these on the MCAT. So let me first define this weird term that you may or may not have heard before, which is triboelectricity. So this is just the transfer of charge between two objects by means of friction, i.e. you take your plastic rod and you rub it with a cloth. And what happens is that these materials have different electron affinities. In other words, when you rub these two materials together, one of these materials is actually going to steal some of the electrons from the other material just based on the fact that it has a higher electron affinity and wants those electrons more than the other material. So the material with greater electron affinity steals the electrons and therefore has a negative net charge after contact with the other material. And then the material with lower electron affinity is positive after contact because some of the electrons have been stolen from it. Therefore, it has a positive net charge. So let's go back to our rod cloth example. So we have a cloth that is neutral at first, and then we take this lucite or acrylic rod, which is also neutral at first, and we rub it with this cloth up and down all around. And what happens is that this cloth actually steals some of the electrons from the lucite rod, and this rod becomes net positive, and then the cloth becomes net negative. And so this brings up an important principle of charge, and that is conservation of charge. And so electric charge cannot be created or destroyed in a closed system. So if we imagine this rod cloth example as a closed system, then we know that the amount of charge has to remain the same, meaning that the amount of charge lost by the lucite rod is actually gained by the cloth. So that total amount of charge has to stay the same, and therefore we can say that this charge is just transferred, not created, and not destroyed in this system. All right, so you take this positively charged rod that you just charged up with this cloth, and you place it near a soda can. What happens? Well, what happens is that you actually induce a dipole within the atoms of the material, which in this case is aluminum. And this causes the alumina can then to be actually attracted to that rod, and it pulls that can towards the rod and rolls, towards the rod as you've seen in the demonstration. And so this brings me to the next important concept to understand regarding charge for the MCAT, and that is conductors and insulators. So conductors allow movement of charge within a material. For example, our soda can in this demonstration is a conductor. It needs these electrons to be able to move around in order for the atoms of the aluminum to form dipoles, which then cause this aluminum can to become momentarily attracted to the rod. On the other hand, an insulator is a material in which no electrons can move in that material. So, for example, you go put this rod up to a golf ball and no dipoles can form because there's no electron movement, and you see no attraction to this rod from the golf ball. The golf ball just sits there and nothing happens. So again, conductors are materials that have electrons that can move around freely. Insulators are materials in which electrons are stuck in place and cannot move around freely. It's important to understand this force that moves the soda can when the rod is placed next to it. This is called an electrostatic force, which is a force of attraction or repulsion between charged particles. And you can imagine the soda can as being a charged particle on the basis that it does form this momentary dipole. So just imagine that that is a charged particle. And these electrostatic forces follow Coulombs' law. Coulombs' law says that the force of attraction or repulsion between two charged particles is equal to some constant K times charge times the charge of particle 1 times the charge of particle 2 all over the distance between these two particles squared. So the most important thing to understand about this equation is the relationship between force and distance. The relationship is a 1/distance squared relationship. So the closer these particles are, the higher the force is, and this has an exponentially increasing relation to distance. In other words, the closer these particles get, the more and more and more force they get, and this increases exponentially as these particles get closer. And it's also important to note that the unit of measure of charge is called a Coulomb as well. So that's important to remember, and that's in ampere per second. So let's put this all together for you. So we have this rod, we have this cloth, both of them are neutral at the start, then you rub them together, and the cloth steals some electrons from this plastic rod. This plastic rod is then positively charged, and then you place this rod near a soda can, which induces a dipole within the soda can, which then causes that soda can to become briefly attracted to this plastic rod, and the soda can then rolls. This force is known as an electrostatic force and is proportional to the distance between the rod and the soda can squared. In other words, the closer I put this rod to the soda can, the higher that force is going to be, the faster that can is going to roll. And so that's a brief introduction into static electricity. Again, the most important things here to remember are that charge is conserved in a closed system. Remember Coulomb's law, F is equal to K, charge 1, charge 2 over the distance between particles squared. Lastly, understand the difference between a conductor and then an insulator. A conductor, electrons can move around freely, whereas in an insulator, electrons are not able to move around freely. All right, so that's a little bit on static charge or static electricity. The next thing I want to talk about is moving charge. So when I talk about moving charge, understand that I'm talking about moving charge carriers. So for instance, you have a moving electron, you have a moving positron, you have a moving charged X, whatever it is. Because charge is some intrinsic property of a particle, you have to have a moving charge carrier. Just an important note. And so a moving charged particle produces a current. And in terms of household electricity, typically current is produced by a flow of electrons. And so in this case, what actually causes these electrons to flow? What causes these charge carriers to flow? Well, that is an electric field. And so an electric field is a force that acts on some charge. Mathematically, it is defined as F over Q, or force per charge. And electric fields are usually shown as these vector fields. And so each vector in this vector field is actually the force exerted by this electric field at that certain point. So imagine taking an electron with a pair of tweezers, putting it on your finger, and taping that electron to your finger. Now you take this electron that you've taped to your finger and you move it all around the field that you're interested in, some three-dimensional space that you're interested in knowing what the electric field looks like. And you move it all around and you measure the force exerted on this electron and therefore on your finger at each of these points. So you take the magnitude and direction of the electric field and you draw all these out for every single point that you just measured, and voila, you have the electric field vector diagram for whatever three-dimensional space that you wanted to look at. These vectors are also known as electric field lines. You may be more familiar with that terminology, but just understand that these electric field lines represent the force exerted on a charged particle within the specific electric field. Now, one important thing to understand here is the directionality of these electric field lines. And so I'm going to go in a second and talk about the electric field created by point charges. But before I do that, I want to talk a little bit about the directionality of these lines. So the electric field lines, in terms of point charges, will radiate from a positive charge and go into a negative charge. In other words, they point at these negative charges, point away from the positive charges. And so One easy way to remember this is to think about what happens when you have the option between eating broccoli, which is good for you or positive, and eating ice cream, which is bad for you or let's say negative for your health. Well, you're placed right in between these two. You have a bowl of broccoli on your right and a bowl of ice cream on your left. What are you most likely to go for? The answer here is pretty easy. You're more likely to go for the bowl of ice cream. And you can kind of think about the electric field in this way. It flows from positive to negative or goes into the negative away from the positive. So again, to summarize, electric field lines from a point charge go from a positive point charge into a negative point charge. The other thing to notice when you just visually inspect an electric field diagram is to notice that the higher the density of these electric field lines corresponds to a stronger electric field at that point. So that's just something to keep in mind here. And the same goes for a magnetic field, and I'll get to that in a little bit, but just know higher density of lines equals stronger electric field. There are two types of electric fields that you're most likely to see on the MCAT. This is the electric field created by a point charge, and then also a uniform electric field. I really haven't seen too many questions or problems on these kind of wacky, funky electric fields like electric field from a wire or the electric field from a ring, or electric field from just these other kind of weird ones. So I wouldn't worry too much about those. What I would know is the equations and concepts related to the electric field of a point charge and a uniform electric field. I'm going to go over those. All right, let's talk first about the electric field generated from a point charge. So in order to establish the equation for the electric field established from a point charge, you combine the electric field equation, which is just that E is equal to F over Q. The electric field is equal to the force at some point over the charge of that point. You combine that with Coulombs' law in order to then determine the equation for this electric field from a point charge. And that is that the electric field is equal to K, which is Coulomb's constant, which is equal to 1 over 4 times pi times emissivity constant. Don't memorize this number. It is 9 times 10 to the 9th newtons times meters squared all over Coulomb squared. Again, don't spend your time memorizing that number. That would probably be given to you on a problem. So, okay, going back to the equation for a point charge, it is equal to that K times the charge of the source, which again is your point charge, all over distance squared or R squared. And so right now, I hope you're thinking, okay, distance squared, what does that mean in terms of an electric field? Well, that distance or that R squared is just the distance from this point charge to any point in space where this electric field is created. So R could be infinity, right, which is an infinite distance away from the point charge, or R could be 1 centimeter away from the point charge. All that's saying is that this is the distance from that point charge to some point in space. And as always with the MCAT, it's really important to understand the proportionalities here. So as you move away from this point charge, your electric field decreases at an exponentially increasing rate. So the electric field is proportional to 1 over the distance away squared. And it's important also to note that the electric field is directly proportional to the charge of the source, which is Q. And this makes sense, right? The stronger the charge of your source charge, the stronger that force is going to be in terms of pulling all these other particles in, which is what the electric field really gets at in the end, right? Is the force at which this point charge either pushes other charged particles or attracts other charged particles. And of course, in this equation, K is constant. It doesn't change no matter what. It's this universal constant. So that doesn't matter in terms of changing an electric field. Real quickly, I want to give you an example of how an electron behaves in an electric field that is generated by a point charge. So keep in mind here that the electric field actually diminishes as you move away from the point charge in exponential fashion. And let's say, for instance, that this point charge is positive. In other words, you have electric field lines going away from the positive charge. Well, you take your electron that's been taped to your finger and you take tweezers, you pull that thing off, you set it in the electric field and you let it go. What happens? Well, it's going to accelerate faster and faster and faster until it collides with that point charge. In other words, it goes against the electric field lines. So that's something to remember here. You have a positive charge that has created electric field lines. They go away from that positive charge, but an electron actually acts the opposite of the field lines. It goes towards the positive charge in the opposite direction as the field lines. So this illustrates an important point to keep in mind, and that is that negative charges will go against electric field lines, positive charges will go with electric field lines. And if you think about what kinds of particles generate these field lines, then it all makes sense, right? You have a positive charge, it's a point charge, generates these field lines going away from it. That means that a positive particle will be repelled by this like charge and will actually flow in the opposite direction, which is the same as the field lines. So it all makes sense. All right, and so the next electric field to understand is a constant electric field. In a constant electric field, the electric field is the same at every single point in space and is equal to F over Q, or force over charge. So then going back to the case in which you taped an electron to your finger, you're moving your finger around and you feel the same force at every single point in space. So that's really the most important thing to understand about a constant electric field. It applies a constant force to a charged particle. So you'll typically see this on the MCAT in terms of solving some problem in which they say, okay, you have a constant electric field. Here's a particle in that field, calculate the particle's acceleration. It'll go back to some kind of mechanics problem. And so you can say, okay, since it's a constant E field, we know this particle experiences a constant force, which means that it experiences a constant acceleration, right? F is equal to mass times acceleration. And then you can use these problems to easily solve for acceleration, velocity at some point, or displacement, any of those. And I have seen them give questions in which they use an electron and you have to be able to know the charge of this electron. So this is a number to memorize here that I'm going to give you. It is the charge of an electron, which is 1.6 times 10 to the minus 19 coulombs. So put that number on a note card or write it on the mirror like you are a sorority sister writing out your New Year's resolutions. Closely related to the concept of an electric field is the concept of electric potential. Before I fully introduce the concept of electric potential, you need to be able to understand the work done by an electric field. So let's go back to classical physics. What is work? Work is equal to force times a distance, right? You're pushing a box over some distance, you use X amount of force and you go this far, whatever. You can then calculate how much work you did on that box. And force, of course, for an electric field is equal to Q times E. That's just rearranging the electric field equation. So then you know that the work done by an electric field is equal to the charge of whatever particle you're moving times the electric field times the distance that that particle has moved. So another good point that I'm going to throw in real fast is be able to manipulate these kind of classical physics equations to fit whatever scenario you're working with, right? You might not at first think that, okay, I can use these classical physics equations to describe the work done by a particle in an electric field. But you can combine the force that you know is being applied by an electric field with the work equation and come up with an equation for the work done on a particle by an electric field. So just a general point there. All right, so back to electric potential. So electric potential is the amount of work needed to move a unit of positive charge from a reference point to a specific point inside the field without producing acceleration. So this is somewhat analogous to mechanical potential energy. You can think of a ball rolling down a hill, right? So you start at a high potential energy and you dissipate that potential energy as you convert it to kinetic energy of this ball rolling down the hill faster and faster as it accelerates. To illustrate what electric potential is, take the following example. You take a positron out of the air with some tweezers, and again, you tape this positive particle to your finger. And you take your finger, you put it in some sort of electric field. And now you move your finger from point A to point B at constant velocity, i.e. zero acceleration. And during that time, you have a change in some kind of potential energy while you do that, right? And this is equal to the work done on your finger. or the work done by your finger. Either way. So it's like pushing a rock up a hill, right? You're changing the potential energy because you're doing work. And this potential energy change is equal to the change in electric potential. So the equation to know here is that delta V, or your change in electric potential, is equal to QED, or the charge of the particle, times the electric field, times the distance that particle has moved at constant velocity.
Thanks for checking out the Prospective Doctor MCAT Basics podcast. Sam's doing a killer job taking you through the most important MCAT topics, but what if you need a little extra help? How does a 5, 10, or even 15-point increase in your score sound? Imagine how your chances at admission could increase. Med School Coach's MCAT tutoring can get you there. With the most rigorous selection process of any tutoring company, we see amazing results. We deconstruct each student, find a plan that is going to work, and help execute it. That's why our students add an average 12 points to their score. Completely physician-run and operated, and focusing on nothing but medicine. It's no wonder over 10,000 past students have trusted Med School Coach to get them through the MCAT and into medical school. Check out medschoolcoach.com today and mention code PODCAST for 5% off.
Another really important thing to understand is that electric field lines point from high potential to low potential. In other words, they point from the top of a hill down to the bottom of a hill. And so, applying that back to how different charges move in an electric field, then you can say that positive charges move from high potential to low potential, and negative charges move from high potential to low potential. And think about a positive charge like a rock. What happens if you drop a rock at the top of a hill? It's going to roll down. It's going to move to the lower potential, the lower energy state, which is the bottom of the hill. For example, on the MCAT, you may see a problem in which you are shown a bunch of electric field lines and you are asked which direction a positron will flow if it's placed at some given point, right? And this should be a give me because you know that a positive charge will flow with the electric field lines. And then as the MCAT does, it might like to throw in a little because and then blah, blah, blah. And so this would be because a positive charge likes to move from areas of high potential to low potential, right? So knowing why some of these things happen is always good because the MCAT might give you, A, B, C, D, where A and D are both, okay, the particle moves with the electric field lines, but then it will say because A, positively charged particles move from low potential to high potential, or D, because positively charged particles move from high potential to low potential, in which case you would pick D. And the biggest place that electric potential is actually going to come up is in voltage. And voltage is a measure of electric potential difference, which is very, very important for circuits, which, as I mentioned a little earlier, is a very, very important part of the MCAT and is deserving of its own podcast. So I'll pick back up on this idea of voltage in that podcast. I hope by the time you're listening to this that podcast is already out, which in that case, after you finish this, go head on right over and listen to it. If not, then it will be coming out shortly. So let's move on to the next topic at hand here, which is magnetism. And I'm going to start with a little bit here. The magnets are really freaking weird, right? You cut a magnet in half and you now have 2 magnets. You cut those 2 magnets in half. Now you have 4 magnets. It's like magnets just keep on reproducing. And not to get too controversial here, but that's magic. And so, for real, if you go back to physics, think about some demonstration you've seen. I'm sure you remember where your physics teacher takes these magnets that can be pulled apart, and they show you this long magnet that has a north pole and a south pole. And then they pull off all these little sub-magnets from it, and each of these magnets then has its own north and south pole. So you get a bunch of functional magnets from what used to be one functional magnet. So let's get into magnets. So what is magnetism? Well, magnetism is just a physical phenomena in which force is applied via a magnetic field. And that's about as deep an understanding as I have on magnetism in terms of what exactly it is. And that's really all you need to know in terms of what it is. Let's talk about different magnetic materials. This is important for the MCAT. there are 3 different types of magnetic materials to know for the MCAT. The first is diamagnetic materials. The second is paramagnetic materials. The third is ferromagnetic materials. So let's start with diamagnetic. So all materials have diamagnetic properties. And this is a tendency of a material to oppose a magnetic field. And in cases where materials either have paramagnetic or ferromagnetic properties, those properties just kind of overrule the diamagnetic properties. They still have diamagnetic properties, but they're just overruled. So that's important to understand. And these properties come from the material having no unpaired electrons. And as I said, diamagnetic materials will weakly be repelled by a magnetic field. On the other hand, paramagnetic materials are materials that have unpaired electrons. And so think back to the lecture I did on atomic chemistry. Remember that electrons will tend to spread out in an orbital before pairing up. And when they're paired up, they will have opposite spins, which goes back to the Pauli exclusion principle. And so what's important to understand here is that these paired up electrons are actually kind of just stuck in place, right? They can't change their spin or align spins or any of that because they're paired up, they're stuck in place. However, unpaired electrons are actually free to orient their spin as they please. So when you have some kind of magnetic field applied to a paramagnetic material with these unpaired electrons, it allows these electrons to actually align with the magnetic field. And what this causes is for this paramagnetic material to actually be attracted to a magnet. And what's important to understand here and what distinguishes this from ferromagnetic materials is that these materials do not act as permanent magnets, but instead are attracted to permanent magnets. All right, so ferromagnetism is the last type of magnetism to know. And in materials that are ferromagnetic, there are also unpaired electrons. So you have to have unpaired electrons. The difference in ferromagnets compared with paramagnets is that there's a tendency for these unpaired electrons to orient parallel to each other to maintain a lower state of energy in ferromagnets. In other words, in ferromagnets, the unpaired electrons actually line up all together on their own, and this causes them to be permanent magnets. And so in order to keep these all straight in my brain, I've come up with a little mnemonic or memory device here, in which I think ferromagnetic, I think of Pharaoh, like the ancient Egyptian rulers. And I think the ferromagnets are the kings of all the different types of magnets, right? They're permanent magnets. So when you see Pharaoh, think king. Then you can compare the prefixes of the other two materials and look at di and then para. Di is obviously a prefix for two. And what else means two or a set of two things? And that is pair. So when I see di, I think of paired electrons, which then makes me think, okay, I'm dealing with the type of material in which all the electrons are paired up. And what happens in this case? Okay, well, I know in this case, this material then must be weakly repelled by a magnet. So to quickly summarize all these different types of materials, we have a diamagnetic in which the electrons of this material are all paired up. Therefore, we don't have any unpaired electrons, and these diamagnetic materials will be weakly repelled by a magnetic field. And then we have paramagnetic materials, and these are materials that have unpaired electrons that line up with the magnetic field. And what happens there is that these materials then become attracted to the magnet, but they are not permanent magnets. And lastly, there are ferromagnetic materials. And these have electrons that are unpaired that actually tend to line up with each other spontaneously in order to achieve a lower energy state. And therefore, they are permanent magnets. The next topic regarding magnetism I want to talk about is the magnetic field, or B. And so magnetic fields are somewhat easy to see. All you got to do is you got to take a magnet and take some iron shavings, which obviously is a common household item, according to our physics teachers, and you throw these iron shavings on the magnet, and you look and you see how they align around the magnet. And if you go Google an image of this, you'll see what I'm talking about, but they line up in this kind of cool pattern that actually shows what the magnetic field surrounding this magnet looks like. The magnetic field describes the magnetic force exerted at these different points in space. It's very analogous to the electric field. We're talking about the force exerted at these certain points in three-dimensional space. And so there's a few different things to take from magnetic fields or to observe from magnetic fields that are very important. The first is that the magnetic field lines are contiguous, unbroken lines. And this is in contrast to an electric field where these lines are all vectors. In this case, they're continuous. They are not unbroken lines. And these lines travel from the North Pole to the South Pole. So they go out of the North and into the South Pole. That's the directionality. And this is kind of easy to remember, at least for me. I just remember that Santa lives on the South Pole, right? Think Santa, South Pole. They both start with S. And when he gets done delivering gifts, he wants to go home, right? So he takes a sleigh and he flies right back home to the South Pole. So anytime you see these electric field lines, just think, okay, this is the same path Santa would take to get home. He'd go towards the South Pole. So that's the second observation that's made regarding magnetic field lines that's important. The third is that, like the electric field, the density of magnetic field lines correlates to the strength of the magnetic field at that certain point in space, or that certain area in space. For example, as you move away from a magnet, the magnetic field lines actually become more spread out. So if you look at electric field line density as you move away from a magnet, you see that this decreases, and therefore the strength or the force exerted by this magnetic field decreases as you move away from the magnet. Logically, that makes sense. So those are a few important characteristics just to understand about magnetic fields and magnetic field lines. Let's next get into magnetic force. So it's important to understand that a magnetic field exerts a force on certain types of materials or certain types of charged particles. We've already talked about diamagnetic, paramagnetic, ferromagnetic materials. And I wouldn't worry too much about forces exerted here, say from a ferromagnetic material to a paramagnetic material. Instead, what I'd focus on for the MCAT is the magnetic force exerted on a moving charge or on a current. The magnetic force on a moving charge follows what's known as the Lorentz force law, or Lorentz's law. And that is that the force is equal to the cross product of the charge times velocity crossed with the magnetic field. So what is a cross product? Well, a cross product is just a way of multiplying two vectors together. But what it really gets at is the point that the magnetic field must actually be perpendicular to the direction that the charge is moving in order for a force to actually be applied. So that's what that gets at. And so if you want to use this equation without having to use the cross product, it simplifies down to QVB sine theta, which is just charge times velocity times the magnetic field times sine of the angle between the direction of velocity and the direction of the magnetic field. And it's all good and dandy to be able to calculate the force that is applied to some current or some charged particle by a magnetic field. But what's most important to understand here is the directionality of the force. And this is where the right hand rule comes into play. Take your right hand, you make a gun with it, and then you stick your middle finger towards yourself. This is also known as the gang sign of the nerds. And, just imagine real fast that you don't know anything about the right hand rule or physics. You walk into an intro physics in college class, and everyone's doing all this weird shit with their hands and looking at each other, and you'd be really confused. So that's something I always kind of laughed at in watching people do the right hand. Watching people do the right hand rule was like, man, if people didn't know what they're doing, people would be like, what the hell? So anyways, so you do that right hand rule and gun with the middle finger pointed at yourself, and this shows the different directions that each of these quantities goes in. So for instance, you have force going in one direction, the velocity of the particle going in the other direction, and the magnetic field going in the opposite direction. And these are all perpendicular to each other. So for instance, let's just say that you're given a problem in which you have some positive charge in a magnetic field and you're asked to calculate the force. So they say, okay, they give you that the particle is moving to the right, so therefore its velocity is to the right. Okay, good. And you know its magnetic field is pointed up. So let's just make the gun with our hand, and we know that going forward, which is our index finger, is pointing in the direction of velocity. The direction of the magnetic field is perpendicular to that, and it's pointed straight up. Then we point our middle finger towards us, and that will tell us the direction of force that is applied to that particle. So when that particle is moving away from us, and the magnetic field is moving up, that particle will actually tend to start to move towards us, because of the force applied by this magnetic field. So that's a quick intro to the right-hand rule, but right-hand rule is definitely something you're going to want to know for the MCAT. So keep that in mind. And don't ever use your left hand, because that'll give you the exact opposite answer of what's right. Another example that you're going to see is the force exerted on a wire with some external magnetic field applied to it with current flowing in a certain direction. So in this case, let's say that they give you the direction of current and the force that is applied to that wire. And the MCAT says you have electric current flowing up the page. They give you this diagram, and so you point your right index finger up the page. And then they say that once a magnetic field is applied, you have a force exerted on this wire that comes out of the page at you. Okay, so right now I am essentially making a gun and I'm pointing upwards, right? And so I know that the current is going straight up and the force is coming right at me. Okay, cool. So then using my middle finger, I can say that the magnetic field is pointing to the left. And boom, that is your answer. So the right-hand rule should be pretty easy. If not, I recommend watching some YouTube videos where you can actually see what people are doing with their hands. Hopefully that brings it back to those great memories in intro physics. And it's important that I note that the force applied to a wire by a magnetic field is actually equal to I times L, which is the current times the length of a wire crossed with the magnetic field. And again, this simplifies down to ILB sine theta. The important takeaway here is that the force, the velocity in the magnetic field are all in perpendicular directions to each other. And you must use the right-hand rule to figure out what these directions are. And a common misconception that I see students miss a lot is in thinking about how a magnetic field exerts a force. So a magnetic field only exerts a force on a charged particle that is moving. In other words, when a charged particle is at rest, no force will be exerted on that particle. No force at all from the magnetic field. It needs that particle to be moving in order for it to apply some kind of force to that field. And this is analogous to a car on ice. So, right, if you have a car and it's just sitting there, in a parking lot, parked on ice, does it slide? No, right? It has to be moving in order for it to slide on the ice. So make sure when you're on the MCAT and you get a question that's kind of trying to trick you and say, we have this point charge that is still, calculate the force exerted on this point charge. And you might be tempted to go use the equations that you know for calculating magnetic force, but think about this car concept. Think that, okay, it's not moving, therefore there's no way that the magnetic field can apply a force to this particle. A magnetic field can also not apply a force to a particle moving in the same direction as the magnetic field. This gets back to the cross product. What is sine of 0? Well, that's also 0. And so when you take the cross product of the velocity cross the magnetic field and they're traveling in the same direction, that's going to equal 0. So, in summary, a charged particle or current must be traveling at some velocity in order for a magnetic field to apply a force to it, and it must be moving in a direction other than parallel. So if the direction of velocity or current is completely parallel to the magnetic field, this charge or wire will not feel any force whatsoever. All right, so that is a brief review of magnetism. Before I go, I want to talk about one real-life medical example that uses magnetic fields, and that is in MRIs, or magnetic resonance imaging. So MRIs use magnetic fields in order to get these nice, clear images from different cross-sectional slices of your body. And this was really important in terms of being able to look and see if there's tumors, for example, or abnormalities within the body without having to surgically go in there and check. So when this was invented, it gave doctors the ability to go into the body without going into the body, if you know what I'm saying. And so magnetic resonance imaging works like this. So first of all, you have a human body that you put into this big kind of circular machine, and you apply a strong magnetic field to this body. And what happens is that the protons in the body, specifically the protons that are bound to oxygen that make up water, and what happens then is these protons spins all align in the direction of the magnetic field. So it's sort of like those zombie movies where, you have a character sneaking around and then they drop something and there's a bunch of zombies around and all the zombies snap their head to the side and they all look at that human. So it's kind of like that. All these protons, all of a sudden their spins all align, boom, right when that magnetic field is applied. And so this results in a net magnetic vector that is in the direction of the proton alignment, which again is in the direction of the magnetic field. So net magnetic vector in the direction of the magnetic field. Then what happens is you apply an additional energy source to these protons. So in MRIs, this is in the form of electromagnetic radiation or radio waves. And so you shoot these radio waves then at these protons, and this actually changes the direction of the net magnetic vector or changes the alignment of these protons a little bit. Next, you shut off this additional energy source. Again, this is just electromagnetic radiation. And when you shut off this additional energy source, the net magnetic vector and thus the protons snap back to their resting state. And during this process, energy is released in the form of electromagnetic radiation. So this external energy source is shut off and these protons go back to their resting state and radio waves are emitted. And then these radio waves are then picked up by a detector in the machine and they are converted to an image. And it's important to note here that changing the magnetic field strength actually changes where these images are taken. So you're able to traverse from the head or imaging, the brain, all the way down to the feet by changing the strength of the magnetic field. All right, so that concludes the podcast on electricity and magnetism. I hope that it helped and you got something out of it. As always, if you liked this podcast, please go rate it on iTunes. Thanks for listening. All right, time for the MCAT Advice of the Day segment. What I want to talk about today is when to start doing practice problems or practice tests, when to stop doing content review and go on and do practice problems or practice tests. I think this is a bit tricky because the tendency is to want to do as much content review as you can at the beginning, cover all your bases, make sure you know all the material that's going to be on the MCAT, and then hit practice problems really hard. What I really recommend is that you start doing practice problems really early, start doing practice tests really early. A big part of the MCAT is being able to sit down for 5 hours straight and be able to take these tests, keep your focus on these tests, and not get fatigued. So because of that, I think it's important that you sit down, maybe even starting as much as a month out, and take a practice test or two every week and really get in the hang of being able to sit there and take these long tests. It's also important to take practice tests early so that you know which areas to really focus your study on, right? If you're scoring really high on the chem phys and biochem, but cars is killing you, then you're going to have to put a little more time into cars. Or, maybe you're not doing so well on the psych-soc section. Well, then you need to put some time into that section. So again, what I recommend is start practice problems early, start practice tests early. Don't spend too long only doing content review before moving on to practice tests. Mix in some practice problems, mix in some practice tests into your daily studying routine.
Thanks for listening to Prospective Doctor's MCAT podcast. If you're a pre-med, you'll want to check out prospectivedoctor.com for tons of free tools, articles, and more podcasts that cover your pre-med life. And if you need help on the MCAT or getting into med school, check out medschoolcoach.com for the experts.